The objective of this experiment was to determine a relationship between the break energy and the wall thickness of parts where the wall thickness has a significant contribution to the cross-sectional area. The product was tested in an IZOD impact tester, and a trend line was found with an R-squared value of 0.7879. When 3D printing parts, there are a variety of options available that can affect the strength of the part. As 3D printing is gaining popularity, especially in practical uses, it is important to understand what the effect these properties have on the overall strength and ability of the part to absorb energy. Some of these different variations include the wall thickness, or the number of layers that the walls of the part have, as well as the infill density, which is a measure of how dense the inside of the part can be. The purpose of this experiment is to explore the difference between these two and what effect each has on the overall ability of the part to absorb energy. Because of the rising popularity of 3D printed parts, it's important for a designer to know what constraints they should take into account when designing a part. For this reason, this experiment seeks to determine a relationship between the impact energy absorption of a part and the wall thickness of that part. This knowledge will allow designers to more successfully create safe parts that will not fail under adverse conditions. For this research to be considered good enough, a relationship that is significantly greater than the noise experienced during testing needs to be determined. However, this relationship will not apply to all designs and shapes, so care must be taken when using this data to not extrapolate to scenarios where the data does not fit.
The governing equation for this experiment was derived to show the relationship between break energy, as recorded by the IZOD impact test in joules, per length of the cross-sectional area of the test specimen in meters multiplied by the width of the cross-sectional area of the test specimen in meters.
To test the break energy of these 3D printed parts, we had a few options to choose from, primarily a Sharpie impact test, a drop impact test, and an IZOD impact test. The Sharpie impact test involves swinging an impact weight pendulum into a test specimen held at both ends. A drop impact test involves strapping down a plate of material and dropping an impact weight from specified height into the center of the impact specimen. And the IZOD impact test involves holding an impact specimen at the bottom and swinging a pendulum to hit the top of the material. So for us, we chose the IZOD impact test because it was the most available to us. MAE LabWorks has an IZOD impact tester available. It also allowed us to create test specimens that were quite small and used a small amount of material. Because of this, we were able to perform a large volume of tests in a short amount of time. Near the end, we were able to perform around 100 tests an hour. Because of this, we were able to collect a lot of data to give us a better distribution of break energies. To use the IZOD impact tester, we calibrated the machine and subsequently placed test specimens in the vise at the bottom. The pendulum was then set at the top with a specified potential energy and swung and hit the specimen at the bottom of its swing path. The safety considerations we made were that everyone wore personal protective equipment for their eyes. Only one person was allowed to operate the machine at a time, with others staying at least a distance of 5 feet away. And the specimens were only loaded and unloaded when the pendulum was fully unlatched and resting at the bottom.
The 3D printer used has a 0.4 millimeter nozzle, therefore the wall thickness of each sample is 0.4 millimeters. The number of walls can be varied, therefore increasing the wall thickness. As can be seen on the plot, there are discrete values at 0.4 millimeters, 0.8 millimeters, 1.2 millimeters, 1.6 millimeters, and 2 millimeters. There are a total of 125 samples that were tested and 25 samples per number of walls. The plot shows a direct correlation between the wall thickness and the impact energy of each sample. A linear regression curve applied to the data shows that the impact energy of the sample increases by 1,898 joules per meter squared per millimeter of wall thickness. The R-squared value of 0.78797 was expected to be a lower value because the testing varied the infill densities to maintain the integrity of the experiment. Future testing can determine the effect of infill density on the impact energy. However, it can be concluded that wall thickness affects impact energy. This means that the thicker the wall of the 3D printed part, the stronger it is.
Using hypothesis testing, the null hypothesis was that the slope equals 0. The alternative hypothesis is that the slope did not equal 0 and that there was a correlation between wall thickness and break energy absorption. This is all with a certainty of 95%. The Z experimental turned out to be 21.29, and the Z critical is plus and minus 1.96. This means that the null hypothesis is rejected because the Z experimental value was much greater than the Z critical value. To calculate the uncertainty of the measurements in this experiment, overall calibration is not available due to a lack of known standards in this particular situation. Instead, error propagation is relied upon. And because the sample sizes are small, the chi-squared approach to find the goodness of fit is not very accurate. But each sample set was visually plotted and confirmed to appear Gaussian. To calculate the uncertainty, two different components were used in this experiment: the bias uncertainty and the precision uncertainty. The bias uncertainty was mitigated as much as possible by calibrating the instruments for impact testing before each testing session. This means that we could rely upon the caliper and the impact tester's error to find our bias uncertainty with an error propagation for a 95% confidence. For the precision uncertainty, two different standard deviations needed to be found. Because only 35 of the samples were measured for their dimensions, a sample standard deviation needed to be used. For the break energy, a population standard deviation was used. With these standard deviations and the appropriate Z-table score, and using error propagation, the precision uncertainty was able to be found. Similar tools were used to determine the uncertainty of the slope. As shown in the presentation, the uncertainty of the slope using the standard slope error is 175,000 joules per meter cubed. Below is a table showing the uncertainty of the values of each bin of wall thickness.
In conclusion, impact energy has a positive correlation with wall thickness. This information should be used for parts where walls are a significant portion of the cross-sectional area. This information is presented at a 95% confidence interval and can be expanded to include more cross-sectional area types, such as wide or flat.
Different design decisions we made for our project include the impact test that we needed to choose. The first one is our IZOD impact test. It works by having a vertical notch sample struck by a swinging pendulum on the same side as the notch. It is repeatable, precise for plastic materials, has built-in data in the instrument, and we have access to it. It is lab-bound, however, and expensive. We chose it because we have easy access, accurate results, and it's very repeatable. Option 2 is the Sharpie impact test. It is a horizontal notch sample struck by a swinging pendulum on the opposite side of the notch. It is also repeatable, also precise for plastic materials, and it does not introduce new stresses. It is also lab-bound and expensive, but we rejected it because we have no easy access and it has less accurate results. Our third option was the drop weight impact test. It works by releasing a weighted bar on a guided rail to strike a flat plastic plaque, measuring the energy required for total failure. Strengths is that it is repeatable, more accurately demonstrates the real-world impacts, but its weaknesses are that it is lab-bound, expensive, no easy access to the instrument, and it requires more material. That is the reason why we rejected it. Our second component was the sample design. Our first option was changing wall thickness, which we selected. The sample design was easy to edit. We can print multiple samples at once. However, it does introduce more stress concentrations into the sample. We chose this because it allows for mass production needed for the project while changing the results. Our second option is changing the print orientation. The sample design was easy to edit. We can also print multiple samples at once. However, it does not work as well with the chosen impact test. We rejected it because it does not work for the impact test chosen.
In calculating the uncertainty for the measurements, 4 different error sources were considered or included. For bias uncertainty, the digital encoder error and the printer error were considered, though the 3D printer's error is negligible in this scenario. For precision uncertainty, the calipers and the impact energy tester were considered and included. Below are statistical tools that were not used in this experiment. Some of those include Chauvenet's criterion for removing outliers. As our sample size was not large enough, nor did we have any outliers to make this necessary, the Chauvenet's criterion was not used. The chi-squared was also unnecessary because it uses expected values that are unavailable in this experiment, as well as not dealing with frequencies. The central limit theorem was also not used because there was not a large enough sample to deem this necessary, as well as the samples are already in a Gaussian form. One other consideration is that a theoretical model was not used because it's impractical for this given scenario, as the actual cross-sectional area of each sample is almost impossible to calculate accurately. Along with that, this experiment shows a relationship, not an actual model to be used in other applications.